besides that
Okay.
we do. So,
Okay.
hey guys, today we're going to be going over, there's a beautiful slide right here, carbon skeleton intermediates going into the TCA cycle. So we've taken an amino acid, removed the nitrogen, the carbon that's left over after the nitrogen's taken off, that carbon skeleton, also called an alpha keto acid, is going to go into the TCA cycle or just a little bit above it. And so we're going to find out how all that works. And then besides that, also, I believe there might be some special products in here. So informal, going to go ahead and just do what we do. So that's what we're doing. Hope it helps. Okay, so now it's just, just a normal session. So, and like I said, this can go just you or however you want to do it. So, with this, I'm going to go ahead and start by taking a look at what she covered. Looks like not too much has changed. That's nice. Okay. So besides going into the TCA cycle, it looks like she's gone over also some of the pathways of between them and the TCA cycle, which makes sense. So I'm going to go ahead and draw up our TCA cycle. So I'm going to go ahead and start with, we're going to skip the citrate and isocitrate because they don't have anyone going directly to them.
Okay.
So we're going to just go straight to alpha keto glutarate. And for this particular lecture, I like to just go ahead and have a little box here.
Mm-hmm.
And also over here, draw a little store. And it's got a sign on it that says GHAT. Alright, there's little doors going in. So, G, H, A, and P. G is going to stand for glutamine and glutamate, which are both going to, so glutamate is the one that these guys have as an intermediate before they reach alpha ketoglutarate. So it's these guys kind of going to glutamate and then glutamate to alpha ketoglutarate. So I'm just going to put glutamine right here. And it becomes glutamate just by the deamination that we talked about last time. So that one should be glutaminase is the enzyme.
Okay.
Okay?
Mm-hmm.
Do you want to go into that more in depth, or does that ring a bell?
No, it doesn't ring a bell.
Okay, no worries. It's possible, I remember that with, I don't remember who it was with, but there was one group that I didn't actually talk about glutaminase, so it might not be your fault.
Yeah, it probably was not.
Alright, so we have, going backwards to the muscles then. So muscles, amino acids get broken into carbon skeletons, and all of their nitrogens get thrown on to pyruvate, which makes them into alanine. Sounding good so far? Okay. That'll go to the liver. Just a bit of review here. That is my most beautiful liver yet. All right. So the liver is going to go ahead and bump those nitrogens off of alanine and put them onto alpha ketoglutarate.
Okay.
And alpha ketoglutarate is that's going to be done. So alpha keto glutar. All right, I'm going to take more room. We're going to do this properly. Okay, so I'm going to go to the picture now that we've made it over there. We're at the liver, and we have alpha keto glutarate. We add a nitrogen, and that is using the enzyme glutamate dehydrogenase. Okay? And that'll add it, and this will make it into glutamate. And then from glutamate to glutamine, glutamate, we are going to use the enzyme glutamine synthetase. So I'm going to put G synthetase. Synthetase. Okay? So that guy's going to take ATP because synthetase. The T in tase means that it uses ATP.
Okay.
Whereas synthase, free.
Free.
No ATP used.
Okay.
So this one is a synthetase, therefore ATP is used. Okay, so that is building up, and it's like we still haven't seen glutaminase. What the heck? Okay.
Okay.
Now we're going to go backwards, and this is breaking it down from glutamine when we're ready to make urea. That's a chromium marker. When we're ready to make urea out of the nitrogen. So glutamine's held on to it for us. Thank you, glutamine. And I might have. I seem to have accidentally donated a marker to another room. I'll go and snatch it later. All right. So this is going to be called glutaminase. So glutamine ACE. Or in other words, cutting glutamine apart. So it's just going to take the nitrogen off, and this is a deamination.
Deamination.
And that is because the nitrogen is going to be released and be free floating.
Okay.
Transamination is when you take it from one molecule and put it onto another molecule. It's never a free nitrogen. That's transamination. You're transferring it between two places.
Okay.
This is deamination, where you are taking it off and then just dropping it into the cytosol.
Deamination.
Yes.
Okay.
So a nitrogen group is called, in Latin or Greek or whatever, probably Latin, an amine group. Therefore, deamination is where the name comes from. Deamination.
Okay.
So the nitrogen is going to pick up some hydrogens, and it'll be floating around, and then that is going to go to the urea cycle, because anytime we're going to end with a free nitrogen, that's bad unless we do something about it.
Okay. Let's say urea. Because that one's toxin.
Exactly.
Okay.
If that's the one that if it gets to the brain, then you have a really fun time for about 4 minutes, and then you don't have any more fun times. So 4 minutes is me making a number up, by the way.
Okay.
So, now, if we want to go from glutamate to alpha ketoglutarate, because there's still a nitrogen in there, right? Here, and I'll finish writing the nitrogen over here. Plus nitrogen. All right. Minus nitrogen, minus nitrogen. All right, this one is going to be actually the exact same enzyme. This guy works forward and reverse, so it's going to be glutamate dehydrogenase, which is really nice.
Okay.
So same guys, different guys.
Okay.
Okay? Sweet. So you can see how glutamine becomes glutamate. And that's actually what we're looking at right here again. Right. And this time we're looking at it not because we're trying to necessarily make urea from breaking down muscle or whatever. Now it's just, oh, hey, we might want glutamate because it's an important amino acid. And so we'll go ahead and bump that off. Yes, it'll still be made into urea, but it's just because we were making this amino acid this time. So same pathway, different reason.
Okay.
What are we after? Are we after the amino acid, or are we after the carbon skeleton that's got some energy while we're starving?
Okay.
Same thing happens, just different reasoning behind the body's actions. All right, so next we'll go ahead and H. That stands for histidine. And for this one, I go ahead and just have a little snake. And besides that, what does histidine sound like? Histamine.
Oh.
And so that is the product that we often will see histidine become. So histamine, and honestly, I just put little red dots that it's like histamine inflammation because I avoid writing words whenever possible. All right. Next, we are going to go ahead and have Arginine. And we'll verify. Yep. And it's the pirate fighting the snake. Alright, so there's our sword. And there's our burly pirate. He's like, back!
Fighting the snake.
Yes, Arginine and histidine. Alright.
Okay, so Arginine. Okay.
Precisely. Arginine has a few different products it can become. I'm not sure if those were ones that you've hit yet. They include, however, carnitine. They include a few others. I think serine is connected to. I'm gonna have to do my transfers again.
Okay.
But it doesn't look like that was part of this particular lecture. Mostly she's trying to get them down in there, and so we can cover that much. And I'll review the other ones for next time.
Okay.
So, but I know that it does something with it's polyamino something. Anyway, so that's arginine. Next we have proline, which is just for P. So proline. And all of these will eventually become alpha ketoglutarate or vice versa.
All of those can become alpha ketoglutarate?
Yes.
Okay.
This particular lecture is a lot of memorization rather than the understanding of a large pathway, which we usually have.
Okay.
Okay. Next, we have, I like to remember it as, MTIV is one way, but there was, let's see, MTIV, S3, there was, I'm trying to remember the acronym that makes sense to everyone else. For me, it was MTIV just because it was fun to say and it stuck.
Mm-hmm.
We'll go with that today. MT, oh, that's right, okay, M3IV. That's what I changed. That way you know which T it is. It is threonine.
Threonine, okay.
Okay. And for the picture that you will want to have right here, it's a little IV bag. What kind of IV is it?
Threonine.
M3. Yep. And it's just an IV bag that someone is having. Okay. So here we're going to go ahead and have methionine, threonine, isoleucine, and valine. Now these guys have a little bit more to them that we will want to hit. And so with the methionine, so they have a number of diseases that they share,
Mm-hmm.
and then there are a few that they don't. So methionine and threonine both have propionic acidemia.
Okay.
Methionine and threonine, we're going to go ahead and put a blue box right here because they both have propionic acidemia. And we're going to put acid there. Next, threonine and methionine also share methylmalonic acidemia.
Methylmalonic?
Methyl referring to methionine is called methionine because it has a methyl group. So meth.
Okay.
And then we have methylmalonic acidemia. Emia, meaning that we're finding this in the blood. Acid, meaning it is an acid or makes the blood acidic.
Okay.
And so we have a methyl group thing. Malonyl, we've seen malonyl-CoA before. Malonyl-CoA was in the fatty acid.
Yeah.
Nice, well remembered. It's a 3-carbon molecule that looks slightly different than pyruvate. And so we have a methylated malonyl molecule that is acidic in the blood, is what this disease is telling us. And you don't need to memorize all of that. I was just breaking it apart in case you ever need to break it apart as a...
Okay.
Which of these multiple choice answers should ask this question? It's probably reaching a little bit too far. Let me deduce from my Latin skills. All right. Which is really helpful. All right. And then isoleucine should share one with, let's see, 8, 9. Isoleucine should share one with, I think, threonine. That is another acidemia. So let's see. Okay. So it is actually these 3 guys that share some things now. We're going to make this a little bit bigger.
Yeah.
So threonine, isoleucine, and valine. Those are the branched chain amino acids. And so they are going to have some pathways in common. So we're going to go ahead and give them, we'll use purple, because purple's a good color. We're going to go ahead and give them their own little box here where they're sharing stuff.
Okay.
So they can have, there's the acid, it's branched chain alpha keto acid dehydrogenase. And so BC-CAD is what that is. So branched chain alpha keto acid right there.
Okay.
I'm not going to write the whole thing out because that's
Branched
obnoxious.
chain.
I'm going to put BC-KAD.
Okay.
Okay, and then for you guys, right there. Okay, so if you have issues with that, one disease that you can get, box the disease for right now, is BC-KAD, BC-CAD. So that is the enzyme that's broken is called BC-CAD is what I should say. I've been saying it's a disease, but that's the enzyme that's broken, and I believe that one leads to maple syrup disease, if my memory serves. So, branched chain amino acid, maple syrup urine disease, when BC-CAD is broken.
Okay.
So, with that, there are 3 different places in their pathways. So they have pathways in their degeneration down to succinyl-CoA. Incidentally, I never did write that up. Succinyl-CoA. Succinyl-CoA is what these guys are eventually going to become. And they have, the branched chain amino acids have a decent pathway to getting there. And there are particular enzymes that can break in those pathways. And so, we have, for isoleucine, it's propionyl-CoA carboxylase. Isoleucine, we're going to go ahead and I'm going to shift this a little bit. Give me some more. Propionyl-CoA carboxylase. Other enzymes that are worth noting is methylmalonyl-CoA.
Do you want a bigger screen?
It's alright. Methylmalonyl-CoA is the only one that I need left. Because two of them actually share that. Valine and isoleucine share methylmalonyl-CoA. So, isoleucine and valine both have methylmalonyl-CoA can break. Okay. Good deal. So, the three enzymes that can break BCCAD, propionyl-CoA, or methylmalonyl-CoA.
Right.
Those are the enzymes. And so those are carboxylase and mutase. So this would be carboxylase is right there. This one has mutase at the end, so they're enzymes rather than the molecules. Mutase. Okay, and that covers the guys that can be broken down to succinyl-CoA. So basically, these enzymes, if they're functioning normally, we can get these guys to succinyl-CoA, no problem.
Okay.
If they're broken, then at this step, or that step, or that step, wherever, we don't get them to succinyl-CoA, and we build up byproducts that are not great.
Okay. So these are all disease?
So if the enzymes work, they're just enzymes.
Okay.
If the enzymes are broken, then we give that a name, and that is a disease.
Okay, okay, so these are just enzymes.
Yes.
Okay. But up here, there are amino acids, right here. Okay.
These are the amino acids.
Those are the amino acids.
Amino acids. And then some diseases and some enzymes.
Okay.
Okay. So, and I am noticing one thing that I would like to verify just to make sure, because these disease names look a heck of a lot like those enzymes, which makes me think that they should be paired, and I don't want to leave you hanging on that.
Okay.
So, in my opinion, this is one of the more information-dense and memorize-y lectures that you get. Thankfully, they don't get much more than this.
Oh, no. This looks like a lot of information to memorize.
It's good times.
Aren't you glad you passed that stage?
A little bit.
But there's always room to learning new stuff.
There is. So, if I can't find it quickly, then we'll move on. But I would like to get you so you don't have to pour through it. I would, oh, there we go. So number 3 does cause, yeah, okay. So propionyl-CoA carboxylase deficiency will cause propionic acidemia. If it's broken, methylmalonyl-CoA will cause methylmalonyl-CoA acidemia. It probably doesn't have the CoA in the disease, though. Acidemia, which means that these, even though they're listed just underneath methionine and threonine in the slides, the fact that the enzymes are involved under isoleucine and valine, and all these 3 pathways kind of mix with each other a little bit, makes me think that even though the slides only indicate it right here, they probably can happen with all of them. Otherwise, those enzymes being there wouldn't make sense for it to only be those guys.
Yeah. Okay.
So that's probably what's going on. All right, moving from there, let's go ahead and next we have fumarate, and this one is pretty straightforward, thankfully. So we're going to go ahead and stick fumarate down here at the bottom. And the way that I like to remember this one is, well, we have phenylalanine. And phenyl sounds a lot like funnel. And then we have tyrosine, and tyrosine sounds like a tire, and so I just make a funnel where the top is a tire. And that reminds me of the two that come out with fumarate. So let's go ahead and make a little boxy thing, and we will have phenylalanine and tyrosine. And for this particular one, there's a good slide that I have always gone back to in my head that she still has, I'm glad. And that one has the pathway listed out all on one slide, showing how phenylalanine becomes tyrosine.
Is it in this PowerPoint or in that? It's another PowerPoint, I think.
I believe it is in this one.
Okay.
Here it is. So, really quick, that one. So, see how it has phenylalanine at the top? Mm-hmm. And then there's that enzyme right there. Oh, look, you've already got those pencil bubbled around. So those are the ones that you do want to remember. It looks like you've already seen it. Okay. There's also, if this one right here is broken, tyrosinase, then that will cause albinism.
Albinism?
Meaning no skin color, no hair color, no color of the iris. Okay. And so completely bleached, no melanin. And so, yeah, so phenylalanine is essential. Tyrosine is not, because phenylalanine can be changed into tyrosine. But if you don't have any phenylalanine, then it's kind of hard to make tyrosine.
What's essential?
Essential as in you have to get it from the diet. So phenylalanine is an amino acid that we can't make. Okay. We have to eat it. Okay. So, and with this one, you can have PKU, phenylketonuria. Okay. If you have the enzyme phenylalanine hydroxylase is broken. Okay. Okay. Because then you build up phenylalanine because you can't get rid of it when you need to. And then that's why people with PKU have to have very specific diets to avoid that amino acid. Okay. Otherwise it builds up and they have problems because they can't break it down at all. Okay. Because that's the only way to break it down.
With phenylalanine hydroxylase.
Yeah. Okay. And so that's what PKU is.
Okay.
We explained what albinism is with tyrosinase. Okay. And I just like to kind of see this slide and say, okay, we got one disease up here, we got one there, and then down here. Tyrosine, let's see, tyrosine transaminase, that one, I think more of this disease down here, so that's a pathway to get down here. Okay. There is a specific disease named Tyrosinemia for that one, where you build up tyrosine in the blood and it can cause some issues. I don't remember having really specific diagnostic picture for what someone would look like.
So it would go from starting here and either go this way, then either that way or this way? Like, I don't...
So this is phenylalanine, the acid, amino acid. Okay. And we can either not break it down at all and it will just become phenylpyruvic acid. Hi. Good to see you, Vanessa. You too. And that will cause issues. Okay. If we have too much of it. If we have the enzyme, we can break it down properly to tyrosine. Okay. And that'll mean that we're all good. So we don't have PKU, phenylketonuria. Okay. So it's called phenylketonuria because you get phenylalanine in the blood and in the urine. Okay. And ketones as well, phenylketo. Okay. And then urea because you find them in the urine. Okay. So, and then the tyrosine is just, what are we going to do with it? We're going to either use an enzyme to go ahead and help make the molecule for skin color and such, melanin pigments, and then, or we can go ahead and break it this way, transaminase, down to here. And this right here alkapnuria. That's a disease that will come up. So that's one of the ones that you would want to know.
Okay.
So this is just a good high density slide in short.
Okay.
So, quiz question. What is the enzyme that will, if not functioning, cause albinism?
Tyrosine.
Yes, tyrosinase.
Okay, tyrosinase. Okay.
Okay. What is the enzyme that will cause PKU?
Phenylalanine hydroxylase.
Yes, hydroxylase. It is.
Hydroxylase. Okay.
All right. And then I don't know if I ever said the enzyme for the bottom one, but so I'm not going to be mean. So enzyme for the bottom one is homogenistic acid oxidase. So for that, you can just think, I would think for that one, I thought of a pair of jeans that had gotten an acid burn, and then the burn was in the shape of an O for oxygen. That's how I remembered that one.
Homogeneous.
And then I just remembered it started with homo. So homogenistic acid oxidase.
Homogenistic acid oxidase.
Right.
Okay.
So, and that causes alkapnuria. So the person who had an acid burn in their genes, homogenistic acid oxidase, because it's a circle, and then his name was Al, and he was wearing a baseball cap. Alkapnuria.
Okay.
That's at least how I remembered it.
Okay.
Go ahead and picture that if you want to keep it. If you don't, toss it out, but picture it now while you have that idea. And then stick it down there at the bottom of that little chart,
So
that particular slide.
Homogenistic acid. Homogenistic
acid oxidase.
So Al is the man's name. He has a baseball cap.
Yep.
With his gene up, but he has a hole in his gene.
It was burned by acid.
And it was burned by acid.
So alkapnuria. Alkapnuria is the top bit of him. And then down below is the enzyme just on the leg, and it's homogenistic acid oxidase.
Okay.
Or you can just practice saying it a lot.
Okay.
So, whatever your preference is.
The pictures are good for me. Imagining stuff. I like to work.
I like the fact that it gives you a double memory, because you have the memory of like, okay, I memorized the one thing, but then you can compare it to the picture and see if your memory is lying to you, which happens all the time. All right, so after that, let's go ahead and hit oxaloacetate, which is my favorite one. Oxaloacetate.
Okay.
So oxaloacetate is pretty dang straightforward. And then for this, it's helpful if you're drawing this particular thing, go ahead and just write those three disease. There's four technically. There's three important ones and one that I always forget about because it's like whatever. But there's PKU, there's albinism, there's technically tyrosine block, tyrosine block, tyrosinemia, same thing, basically means you have a lot of tyrosine in the blood.
Okay.
And then you have alkapnuria. And so if you just remember, there's a disease there, there's two diseases on that little fork, and then there's one disease at the bottom, it really is good for that. So over here, oxaloacetate. What is an ox? It is an animal. So another word for donkey is ass.
Okay.
And so oxaloacetate goes with aspartate and asparagine. So all the animals go together.
Okay.
And so this one, I don't even box that way. I just go ahead and have all the animals together. I can't draw a donkey, so those are donkeys. Alright. And those will just be broken down into oxaloacetate. So the way it would look, asparagine to aspartate to oxaloacetate. So you can see asparagine, aspartate, those are just like glutamine, glutamate, where they go down. So this is the only other amino acid that can hold 2 nitrogens.
Okay.
And I doubt that'll be, well, you never know. I shouldn't try and predict what your questions are. I always found that if you just understood it and went in, then it was okay. And then I never remembered what the heck she asked afterwards. So
yeah, me neither.
Right. This next one is really fun. So this one is going to be it goes, so there's 3 gliders soaring from an AC unit, and then it goes down to, is that going down to 3 gliders soaring from an AC unit. Oxaloacetate has already been used, so this should be like, I don't see a pyruvate there. Well, 3 gliders in, where is it? I'm sure I could figure one of them, but 3, yeah, it is pyruvate, cool. That's the AC. Okay, so we've made it around the circle. Let's go ahead and have pyruvate, which is going to be outside the mitochondria, so we're going to have pyruvate. And the way that I remember all the guys that become pyruvate is, this is going to be hello.
Hi.
Okay, so this is an AC unit, and here's the little grill with the fan.
Okay.
And coming off of the AC unit, we see a really dumb marker that I picked up off the floor for some reason. Alright. We see 3 strings have been tied to it, and on those strings are little gliders. The AC unit is blowing into the wind. So, this is 3 gliders soaring, AC, being blown by an AC unit. And I believe that it was a 3 gliders soaring. And it is a crummy AC unit, or there you have it. All right. Or you can just remember that there's 2 C's. So,
okay.
I think is what it was. Let's see. There's only 1 C, so there's something else that's tickling my brain. There's supposed to be, but they don't have it listed, so it must have just been some kind of little detail. All right. So 3 stands for threonine, which we have seen before.
Yeah.
G stands for glycine. So glycine. S stands for serine. A stands for alanine. And C stands for cysteine. And all of those are going to be able to turn into pyruvate, and that tells you that these are going to be glucogenic.
Glucogenic.
You can make glucose out of them.
Okay.
because they are going to pyruvate, not to an intermediate in the TCA cycle.
Okay.
The intermediates in the TCA cycle also actually, most of them, let's see, those should be glucogenic too. It's acetyl-CoA that's not glucogenic. Let's see here.
Yeah.
Yeah. Acetyl-CoA and acetoacetyl-CoA are ketogenic.
Okay.
So
pyruvate, oxaloacetate, fumarate, succinyl-CoA, and alpha-ketoglutarate are all
glucogenic.
Glucogenic.
And that's because the way that we make new glucose is we're going to take some oxaloacetate out and we're going to turn it into pyruvate. But that means the oxaloacetate has been removed from the cycle. Now, if we made a new oxaloacetate, either by making an alpha-ketoglutarate or a succinyl-CoA or whatever, and then sending it through the cycle until it became oxaloacetate, because that's what it will eventually become, or we made it directly, whatever, somehow we have an extra oxaloacetate, then taking one of those out of the mitochondria, totally fine.
To make pyruvate.
Yeah,
okay.
And then it turns into pyruvate. We still have the ones that were there before we did anything and are still there after we've done everything. It's still all the same. It's all fine.
Okay.
If we took oxaloacetate without making any new oxaloacetate, then that would break this cycle because you wouldn't be able to go through anymore, and basically you'd be removing your ability to make ATP.
Okay.
And so these are glucogenic because you can make a new oxaloacetate. Now, the reason it's like, well, okay, so everything's glucogenic. Well, there's acetyl-CoA. Acetyl-CoA cannot turn itself by itself into oxaloacetate.
Okay.
It has to join oxaloacetate to even get into the cycle. This whole cycle is literally just to burn those 2 carbons from acetyl-CoA. And we can't burn acetyl-CoA if we have no oxaloacetate to hook it onto to run it through.
Okay.
And so that's why acetyl-CoA, since it can't make another oxaloacetate out of itself, it's ketogenic.
Okay.
Anything that can end up as oxaloacetate or pyruvate, well, those can end up as pyruvate. Acetyl-CoA can't. That's why it's ketogenic.
Okay.
Make sense?
Yes.
Great. That is probably the most difficult concept out of the entire thing. So
because it went into pyruvate and acetyl-CoA, and acetyl-CoA cannot go to pyruvate. That's why they are ketogenic.
exactly.
Okay.
Because they are only 2 carbon molecules.
And pyruvate is a 3 carbon.
Is a 3 carbon, and oxaloacetate is a 4. And so you can't just magically make acetyl-CoA become oxaloacetate.
Okay.
And we don't have any enzymes to like bind them together in the right way. If you were like, well, what if we took 2? Well, that'd be great, but we don't. So
acetyl-CoA is 2 carbon. Okay, yeah.
All right, so hopefully this was more of a memory and talking about ways that we can try to picture how they bleed into each other than an understanding. That is the majority of things. The 2 that we didn't cover are the ketogenic, which are acetyl-CoA and acetyl-CoA.
Okay.
And so those ones you will want to look at.
Okay.
But that's glucogenic.
Okay.
So besides that, we talked about some of the diseases. And I'm trying to see if there's anything in particular. I know that for the second half of all of this, there is a video that I made that's a TA session, and it was shortly after I had reviewed all of this a little bit more in depth. And so I do have the diseases in that particular video. We went over and hit most of them. I think that there's a couple diseases in here.
Okay.
And if you can just link, you now know how they get to the cycle. That's the main point. If you know which one's being broken causes which disease, that's the rest.
Okay.
And so it's really just like, oh, Serene has this disease.
Okay.
Okay, great. And just pencil that in, and then you'll be done with the lecture.
Okay. Well, thank you so much, Taylor.
Yeah, no worries.
A walking miracle.
Hmm?
So you're like a walking miracle. All your information is just like stored and you just pull it out.
Oh, especially when you give me the slides, yeah. Just
Yeah.
pull it out of the
Hey, no one has to know. Yeah, but at least you can like recall everything back from what you did learn.
Yeah, that's the idea. It all gets up there eventually. We'll all get there.
Dr. Elton Johnny